Wrapping up this section, we're looking at exponents or powers. And just as multiplication is a shorthand way to represent repeated addition, when we use exponents, we are describing repeated multiplication. So for instance, if you had 4 times 4 times 4 times 4 times 4, instead of writing that out, we can simply write 4 to the 5th power. So this power or exponent tells me how many times I'm multiplying out my 4. We have different rules and properties for exponents, just like we do for addition and subtraction and multiplication and division. We have multiplication rules, and that says that if my base is the same, so the base is what we're repeatedly multiplying, if my base is the same, I can add exponents. So for instance, if I have 4 to the 5th power times 4 to the 7th power, that's the same thing as 4 to the 5 plus 7 or 12th power. That should make sense. 4 to the 5th power would be 5 fours. 4 to the 7th is 7 fours, so in total you have 12 fours, so that should make sense. The next one happens when our bases are different, but the exponent or the power is the same. So the second one, if you had, let's say, 4 to the 5th power times 3 to the 5th power, this is the same thing as 4 times 3 to the 5th power. Then our third one here is we're taking an exponent and raising it to another exponent. So in this case, if you had something like this, 4 to the 5th, let's say to the 3rd power, that is the same thing as 4 to the 15th power. And this one should actually make sense as well if you think about it for a moment. 4 to the 5th is 5 fours, and you're doing that 3 times. Okay, so you have 5 fours, then another 5 fours, and then a third group of 5 fours, so that's a total of 15 fours, so 4 to the 15th. Those are our multiplication rules. We also define 0 as an exponent. Anytime you're raising a non-zero number to the 0th power. 0 to the 0 power is actually undefined, but anything else to the 0 power is just defined to be 1. And then to finish these rules and properties, we've got some division rules with exponents. So our first one, we have the same base but 2 different exponents, but we're dividing. So if I have 4 to the 5th power, for instance, divided by 4 to the 3rd power, we end up with 4 to the 2nd. We just subtract our exponents. Okay? And this should make sense as well if you were to write it out. Let's say I had 4 to the 5th divided by 4 to the 3rd. So some of these 4s are going to cancel out. What's left? 4 times 4, 4 to the 2nd. Then our second one deals when we have the same exponent but 2 different bases. And what this tells us is if we had a fraction, let's say I had 4 to the 3rd power over 5 to the 3rd power, I could rewrite that as the fraction 4/5 to the 3rd power. Either way, I have 4 times 4 times 4 in the numerator and 5 times 5 times 5 in the denominator. So that one should be pretty straightforward. And we're going to use some of these properties real quickly to rewrite these 3 expressions with a single exponent. So the first one, we have 4 to the 8th power times 7 to the 8th power. So we have the same power, the same exponent. So what we can do is we can think of this as 4 times 7, that product to the 8th power. So this would be 28 to the 8th power for that first one. The second one, we have the same base, but to two different powers, x to the 7th times x to the 9th. In this case, we just add, so we get x to the 16th power. And in the third one, t to the 3rd power raised to the 4th power. So we're raising an exponent to another exponent. That's when we multiply our exponents. So we end up with t to the 12th. That wraps up this section, and that's going to also wrap up chapter 2. This was a long chapter, a lot of information, but you're done. Good job.